Okay, hello everyone. Welcome back. So last time we were comparing rates of effusion slash diffusion, and we can use the relative speeds of molecules to determine and the rates of effusion to determine actually the molecular mass or molecular weight of an unknown compound. So we did that last time. Okay, so the last part of chapter 5 is where we've been talking about how gases, how they kind of behave ideally here. They have no volume, and they also have no intermolecular forces, or what we say attractive forces that keep the particles together. We assume that they're virtually negligible because they don't interact as a fluid or as a liquid, right? Or as a solid. So they don't really take shape. We assume the particles are independent of each other. Okay? So, in reality, though, chemistry is a science of no absolutes. There's never a situation where you can say, oh, this always happens, or it's always this case. That's not possible. And that is what makes chemistry very challenging, and I think very intellectually stimulating, and keeps scientists very curious. So there's always an evolving science, just like with everything else: biology, physics, geology, stuff like marine. I guess you could say like marine biology too. Everything. And so science is pretty much you're always learning new things um, about fundamentals and about other stuff as well. Okay, so the behavior of real gases, so it usually agrees with our predictions of the ideal gas law, but that's within like a certain it's kind of like within 5% at normal temperatures and pressures. So it's okay to predict 5%. It's okay to predict gases with the ideal gas law at at normal temperatures and pressures, roughly speaking. But we see a problem here at low temperatures or high pressures. Real gases, they tend to deviate from ideal gas behavior. So the study to kind of account for this, Johannesburg van der Waals. If you know what van der Waals force is, he's a chemist who developed an explanation for these derivations. Actually, I'm not sure if it was a chemist or a physicist. He might have been a physicist, but I think he was a chemist. But let's see here. Yeah, he was a physicist. Yeah, but he worked with thermodynamics, so he was a very important figure in that field, developing our understanding of it. Okay, so we tend to have these derivations at low pressures and um, high pressures and low temperatures. Because at high pressures, right, they um, they tend they tend to occupy a significant amount of volume now, since the volume at high pressure, the volume of the space is really big. So the amount of space a gas occupies now becomes significantly important. If we look at this figure on the right here, at low pressure, the volume of gas particles may be very small, but at high pressures, it's going to be a large percentage, and we can see that drastically in this picture here. Okay. All right. So, number one, gases occupy volume because, and because of this, they are not quite as compressible at high pressures, right? So, at high pressures, gases they tend to occupy significant volume, so they're not able to be compressed as easily. Okay, so to account for this, we say the real the volume of a real gas at high pressures is sometimes larger than expected from the ideal gas equation. So we assume that for ideal they are not as large, but they may be at real at high pressures. Okay, for actual gases. We call it ideal gas because it kind of behaves like this model, and it kind of lets us predict some properties, but we can't always do that. Okay, so the correction for the volume term looks like this. So we have a volume term, and then we're going to say, okay, at very high pressures, the volume is going to be really small, so we need to subtract by this factor here, and this has to do with the volume or size of gas molecules, and N refers to moles. So for every molecule you have there, you need to account for each volume of gas of a gas. So each particle is important. Okay. So when we have low pressure and the volume is large, this correction here is not going to make a difference in the equation. So usually at normal pressures, like atmospheric pressure, high volumes, you have a container that's several liters or several volume units. That correction is not going to make a big of a difference. However, if you have really small pressure, really small volumes, you're going to have very high pressures, and that can affect the behavior of the gas. So that volume term now becomes significant when the pressure is really high, and when the volume is very small. Okay. So at high pressures, when the volume of the gas is small, the MB term does correct for the fact that the volume of the gases is larger than expected from the ideal gas equation. Because here we're assuming that the volume from the gas molecules do not occupy much. So we assume that the volume that the volume of our system is just the container itself. But when we have now a very small container volume, the volume of gas particles will then tend to occupy a significant portion. So that's why we make that correction. Okay. So point number two. So we assume there's no force of attraction between gas particles. Well, that is baloney. That's not true. Because this would make condensing gases impossible. There is some intermolecular forces, right? They're just not as strong, so we need to bring down the temperature, and when we do that, they do form a liquid. So helium does form a liquid if you bring it down to a certain temperature, very low temperature, however. So there's a small force of attraction between gas particles that holds the molecule together. So this is usually the case at low temperatures, and the pressure of a real gas is sometimes smaller than expected for an ideal gas because we take into account these forces of attraction, right? All particles have electrons, they have a nucleus. The opposite charge attraction does attract molecules together. That's how, pretty much all matter is composed. These attractive forces, so it's a natural force in our world. And it's probably influenced by also, the other physical forces like gravity. The force of attraction to everything else is probably due to the overall attraction to the center of the Earth's gravitational field. But that's just something to think about attractive forces. Okay, so to correct this point here, van der Waals added a term to the pressure in the ideal gas law equation to account for this pressure here. So the pressure, it will look like this. So the pressure now, the pressure, it looks like, let's see here. So we add a term here to indicate that at low temperatures, there's going to be an additional force to the pressure, and that has to do with the attractive forces um, to the between the gas particles. But I think it should be, let me see something here. Okay. Okay. So he added that. He added this term because the pressure is going to be lower than expected. To account for that, you need to add this unit here to to account for that decrease in pressure. Because when we add pressure, so the pressure is actually going to be lower than expected. So that's why that term is addition. So to kind of account for that difference in pressure, this term is added. And as we know, remember when we saw earlier that pressure is also equal to the amount of moles divided by the volume here. And I think we square it just because it has to do with like say you're moving in one direction, right, and there's attractive forces in two other directions. I think they square it because of gas particles in three dimensions. But or it could also just be a expression here that kind of corrects the decrease in pressure. So it can also be something totally just mathematic. Okay, but don't worry too much about this. Just be aware that real gases do not behave like ideal gases at low temp and high pressures. Okay. So at normal pressure, temperatures and pressures, right? We use the ideal gas law to describe the behavior of gases, right? PV equals nRT, where the pressure and volume are ideal. Pressure, there is no, intermolecular forces or forces of attraction between gas particles. So the pressure is ideal, is not going to be influenced by other gas particles. And then the volume is ideal because the volume we say is negligible, and the volume occupied by the gas is going to be negligible. But the volume of a real gas, we know that some of the actual volume is going to be taken up by the gas, so we have to decrease the volume with that correction there. And then the pressure here is going to be lower than ideal, so then we have to correct the decrease in pressure by adding this term in the ideal our gas ideal gas law equation here. But let me just see here. Let me just check something here, just to make sure I got it right. Okay. Yeah, so okay. Let's see. Yeah, so that's why we add that term. It's because the volume is going to be the pressure is going to be smaller than normal. So to correct for those attractive forces, we need to add that an squared over v squared term to correct for attractive forces, and the minus mb corrects for volume of particles because it measured the container volume. You have the container volume, right? But to correct for it, you have to take into account NB, which is the volume of particles. So the volume is actually going to be significant there, and it's going to decrease. Okay? All right. So we talked about that. So, so what? Why? So this becomes pretty important when we think about the properties here. So I'll show some data in a second. Okay. So, but under other conditions, right, we see that under normal conditions we can use the ideal gas law, but when we have really low temperatures and really high pressures, we can use the van der Waals equation. So we will have to use this very well, I won't say very, but this complicated equation here. So the pressure of the real gas, volume of the real gas, and we plug those into this equation and solve for any variable we may need. Okay. So here are some constants for the van der Waals equation. These will be provided if we ever see this type of problem on an exam or maybe in a workshop. So here's the constant for A and B. So A refers to the pressure correction, B refers to the volume correction. Okay, so let's look at this figure here. So we see the ideal gas law predicts that plot of our PV over RT should equal 1, right? So our ratio of pressure and volume divided by RT, that ratio should be 1. That's ideal gas law behavior. Okay, so we assume pressure and volumes, they don't have any corrections here. We assume that it's going to be ideal. So that straight line is ideal. So any derivation from that straight line is going to indicate some other, it's going to indicate derivations or deviations from the ideal gas law. And we see that these lines here, they do get, so CO2 is a very peculiar example, but as you see here, at low pressures, and see at low pressures the ratio is close to 1, but as we increase the higher pressures here, several atmospheres above atmospheric, we see that the gases tend to deviate from ideal behavior, and that's because gases tend to behave differently when they're under extreme conditions, so extreme pressures. So we see here that they don't always behave like according to the ideal gas law. So that's why when we see these problems, we don't give you like ridiculous temperatures like -500 or negative or 500 atmospheres, and it's because the behavior of gases can't be easily predicted that way. Okay, so it's a straight line because at constant t would cancel out, and then PV should also be a constant for any gas, right? So you have a higher temperature, you're going to have a higher volume, larger volume will have a lower pressure. So that ratio should stay the same. But it tends to not stay the same because these gas particles, they're all different. They have different volume. They can occupy different volumes at higher pressures, and they can have different pressures depending on the intermolecular forces or forces of attraction between the gas particles. Okay, so here, okay, so this data is for H2 and N2 at 0 degrees, and then CO2 at 40 degrees here. So yeah, it's pretty interesting here that these gases, they don't always behave as we kind of taught them to you guys, to everyone. So chemistry, you can't always predict everything. Okay. All right. So to get a kind of sense what this force of attraction is for the A value for the van der Waals equation, you see here carbon dioxide has a pretty high boiling point relative to many of the other gases here, and that's because it has many more molecules and it's heavier. So the more heavy a gas is, the higher the boiling point. And we'll cover this, but the more polar something is, so polar meaning you have charge separation within the molecule. One part of the molecule is partially positive charge, and one part of the molecule is negatively charged. It can form different, like charge distributions in the molecule, and that can attract and form forces of attraction of different strengths between like molecules. Okay, so we can use the boiling point as a measure of the force of attraction between the molecules. So it's not surprising that there's a direct correlation between the van der Waals A constant, which measures the attraction between gas particles, and the boiling point of the compound that are gases, right? So we see here that the higher the boiling point, the stronger the attractive forces, or for the A constant, and that has to do with the attractive forces between gas particles. Okay, so that's the ideal gas law. The real gases. Okay, all right. So to wrap things up, we're going to finish this lecture by showing an example of how a real gas, the ideal gas law equation, can't be applied to a gas at very low, high pressures. Okay, so we'll do the last exercise here, and that'll be it for chapter 5. So I'll see everyone in the next video.